Hi, so I'm back for another video, and today I just have an example problem I want to go over. So the problem is this. Suppose we have a function g, which is continuous and satisfies the following condition that the absolute value of f of x is less than or equal to the absolute value of x for all x. We need to show that g is continuous at 0. And so if you watched my last video and learned anything about the delta epsilon definition of a limit, that is going to come in handy because we're going to need that. So our goal is to show that g of 0 is equal to 0. And so how we do that is using this new definition of a limit. So what does g of 0 equal to 0 mean? Well, for something to be continuous at 0, it means that the limit as x approaches 0 of g of x equals 0. And this is pretty much the definition of continuity. So if this is true, then we know that this is true. And so how we prove that the limit as x goes to 0 of g of x is 0 is by using the epsilon delta definition of a limit. And so if we recall that statement, it would be for all epsilon greater than 0, there exists a delta such that if x minus a, where a is 0, so if x is less than delta, then f of x minus L, our limit, which is 0, so minus 0, is less than epsilon. Okay, so we have this. So great, so we've written out our delta epsilon statement. So now what? That is a good question. So we use this really useful fact that f of x is less than or equal to x for all x. And so really all we need to do, this question is quite trivial. We just let delta equal epsilon, all right? So we let delta equal epsilon, and if delta equals epsilon, then we have x is less than delta. Well, then we know if delta is epsilon, then we know that, or first, we should notice that x is greater than or equal to f of x. So we know that this is true, right? So we note this first. So we know this, and we know that x is less than delta. Well, if we let delta equal epsilon, then we know that this is just less than epsilon. And so we've shown right here that f of x is less than epsilon. And so now that we know that this statement is true, we know that this limit is equal to 0, and so we can just conclude that g of 0 equals 0. So we've shown this true. That's all we have to do. And now for a second part, the second part of the problem is to show that, is to come up with another function f, which is where this is not true for any a not equal to 0. So we need to show that it's continuous only at a equals 0. And so the function that I propose is, you can see this. We let f be 0 when x is irrational. We let it be x when x is rational. Okay. So this is a very weird piecewise function. You may not have seen it before, but it's very common in like higher level calculus. Anyway, so it looks like this for all rational points, but then this is like an infinitely dense line, but then it's also infinitely dense across 0, and so it like switches back and forth between this y equals x line and this y equals 0 line. Okay, so it's a very interesting function, but we see that it's continuous at 0 because this function converges to 0. Yeah, it's only continuous at 0. But if we look at anywhere else besides, we just take epsilon equal to whatever this distance is, and divide it by 2. I haven't gone over how to like disprove a delta epsilon definition, but you just need to find like an epsilon that it doesn't work for. So whatever this is, just divide it by 2, and since this is infinitely dense, in your delta neighborhood there will both be a point here and here, and not like both of them can't be in your epsilon neighborhood, if that makes sense. And so since it's not within the epsilon neighborhood, this statement doesn't hold, and so we get our contradiction. And so yeah, this is a counterexample to this original question. So yeah, that's all I have for today. So thank you. Let me know what you want to see next.